Hello and welcome to the second lecture on financial mathematics for actuaries. In today's class, we are going to learn simple and compound interest. We have already learned something about simple and compound interest. Before moving on to the second class, let us revise what we have done in yesterday's class or the last class. So we typically introduced one basic concept which is called time value of money, which I also mentioned that money has some dimension in time. So now you understand, whenever you are talking about money, you should look at in what time frame you are talking about money, and that will decide the amount or the value of the money that you are talking about. For example, if you are talking about 100 rupees today, they cannot be same as 100 rupees 1 year later, right? So this is the important notion, and based on this notion, in order to understand how the value of money is depreciating as the interest is earned, we defined two notations. One was capital AT, this was your amount function, and the second one was small at, which was your accumulation function. So keep these two functions in mind, and then we will develop our analysis of simple and compound interest based on these two functions. Also, they have some specific relations which we covered in the last lecture. Okay, so now let us discuss our today's plan, what we are planning today. So first, what we will do is we will define an effective rate of interest. So essentially, you have money in the bank and you are earning some interest, okay, and then on that amount, what interest you are earning may differ, because the way the bank pays the interest differs. Some banks pay monthly, some banks may pay quarterly, some banks may pay annually. So based on these, we have different interest rates, and now we need to if I want to understand the interest rates, I need to understand how much I have earned in an year or whatever is my benchmark period, correct? So in order to understand that, we need to have a concept of effective rate of interest. That's what we will discuss in today's class. Then we will again revisit our simple interest rate model and derive it and see some more features of this simple interest rate models. Then we will go to the compound interest rate model, see the similar features, and we will understand these things from the perspective of the effective rate of interest that we have designed, and then we will see if there are some possibilities where simple interest can pay you more than compound interest. So this is that we will discuss in the crossover trap towards the end of the class. So the reference mapping for our course or this particular lecture is Browerman section 1.1 and Chan and Say sections 1.2 through 1.4. I prefer after doing this class, you read the parts of these sections. Let us begin with today's venture, and to begin with, I will pose you a simple understanding that we have developed yesterday. So I have an amount function A0, it's some amount. Yesterday we have taken it as a principal of k, today it's A0, and then at the end of period 1, I will have accumulation function giving me some value A1. And in yesterday's class or in the last class, we discussed what will be I1. I1 will be essentially A1 minus A0. right. So this is the interest that is accumulated in one time period. This is not an interest rate. This is the accumulated amount or the interest that you have earned. Now, when I want to talk about the effective rate, how will I talk about effective rate? I will benchmark my capital or initial capital, which is given by A0 as the reference point, and how much I have earned when I invested A0. That's the idea. So, A0 is my principal in this session, and then I will use this interest rate I, which will be equal to the interest that I have earned, which is I1 upon A0. You can rewrite it in a better form like this: I is nothing but A1 minus A0 divided by A0. So this is the interest that I have earned, or the effective rate I have effective rate of interest that I have earned during the period 1. Okay. So now when you look at the single period, the calculation looks easy. Also you should remember that this will be a decimal number, not a percentage number. For let me demonstrate that with an example. For example, I have an initial capital of 100. At the end of 1 year, I have not done any other transaction, but at the end of 1 year, this capital became 110. Okay, so my A0 is 100 and now it has become 110. So what is my I1? I1 according to our definition is A1 minus A0, and that will give me 1110 minus 110 minus 100, that will give me 10, right. Now according to this formula, I will put small I equal to 10 upon A0, okay. So that is 100. So 10 upon 100, which will be given as 0.10. So it is in decimal terms. When I talk about it in percent terms, it will be 10% rate of interest. That's what is mentioned here. So whenever you use this formula, you will get the interest rate in decimal terms, and you have to always convert it into a percentage terms in order to communicate it to general public. So it's 10% rate of interest. Okay. So now we are clear about effective interest rate over a period of 1. Okay. So now this period can be yearly period or any period for your as per your requirement. Okay. So now, because this involved some 100 rupees calculation, let us relate this to our accumulation function, where we started with A0 equal to 1, and then whatever amount you accumulated will be A1. The basic underlying principle remains the same. So all other calculations will remain the same except for I have 100 which will be replaced by 1 now. So my I will be A1 minus A0, which is again 1, divided by A0, which is again 1. So here you will come up with the easiest possible solution, that is because this is 1, your I is essentially A1 minus 1, and therefore your 1 plus I will be A1. Okay. So effectively what I am saying, if I start with 1, my A1 is nothing but 1 plus I. Okay. So this is the underlying principle that will operate. Therefore I will get accumulation function in this term. So for period 1, both simple and compound interest will be same. Okay, because compounding only happens annually, or the period that you have chosen over that period, and because the period is 1, this will be same. The interest, so 1 year base case is very easy, we didn't struggle. Now you look at multi-year base case. So here is the idea. So you choose the model of AI to be AT to be simple interest. That means if you invest 100 rupees, and the bank is offering you 10%, what you will get? You will get 10 rupees every year. Interest per year is 10. However, your principal is going to be 100 rupees, correct? So you are every year getting 10 rupees, 10 rupees, 10 rupees. However, the interest that you are earning will remain idle, because you are choosing a simple interest rate model. After T years, the amount that you will earn will be T times I, as we have seen in the last class as well, right? So the formula that you will come up with, this I have derived in the last class, is AT equal to 1 plus IT. If I choose the principal to be 1, it will be 1 plus IT. If I choose the principal to be 100, it will be 100 times 1 plus IT. That will be my accumulation function. That will be my amount function. This is my accumulation function. So now let us focus on this slide, which is basically revealing the hidden flaw in the simple interest rate model. What was the simple interest rate model? The simple interest rate model essentially says that you will earn interest only on the principal that you have invested. It doesn't matter how much sum you are accumulating afterwards. So in the first year, you have 100 rupees and you have 10% simple interest. At the end of year 1, it's natural to earn 10 rupees on 100, and therefore based on this formula that we introduced in the last section, this will be equal to 0.10, and that gives me return of 10%. Let us move to year 2, which is very simple. Now again, in the period 2, what you have earned is I2 upon what was the amount that is available, that will be A1. Now A1 is 110, you have earned 10, so this will become 10 upon 110, which is equal to 9.09%, which is 0.0909. Okay, so now you see there is a clear cut problem here that you are earning less. Now I will reveal you the starking difference. You fast forward this calculation to year 10. What happens? You will still be earning 10 rupees on the 100 rupees that you have invested, and now your I10 will be 10 rupees, and it will be compared with the capital that you had at end of 9th year, which is A9, and that will give me 10 upon 190, which is equal to something like 0.0526. So 5.26%. You can see initially you started earning 10%, but as you are accumulating capital, because your interest earned is not earning the money, you are essentially getting effective interest rate of 5.26% only at the end of year 10. How did I come up with these formulas? It's very simple. So essentially, if I have I, which is the interest rate that is being earned using the simple interest rate principle, then for year 1, A1, what will it be? Whatever amount I have, A0, the accumulation will be I times A0, correct? So accumulation will be I times A0, that I is 10%. In the next year, which will be A2, because I am following this simple interest rate model, there won't be any interest accumulated over here. It will be A0. I am just reframing this. into 1 plus I plus I times A0. So that we have actually translated into A0 into 1 plus 2I. In similar manner, if I continue like this, my AT will be A0 into 1 plus T times I, correct. So when I am calculating the effective rate of interest on the capital, I will essentially look at it at the end of T year period. Every year I will calculate AT minus 1 upon AT minus 1. Okay. So this is the annual calculation that I have to go through, and if I go through this annual calculation, what I get, because AT minus 1, AT is A0 times Ti, minus 1 is T minus 1 times I. So I will get I times A0 upon AT minus 1 is A0 times 1 plus T times I. So this A0 gets cancelled, and I get that effective interest rate that I am earning is around I by 1 plus T into I. Okay. So that's the mathematical result. So if I look at any nth time period IN, the effective rate of return in the nth year IN decreases over time for simple interest by this particular logic, which I have just now shown you, correct. So that's the idea. And here I think I made a small mistake, because it was T minus 1, this should be multiplied with T minus 1. Okay, this is T minus 1 times I. So that's the point here, and that is what I have revealed in this particular formula. So this is the mathematical result, which actually tells you how your interest rate decays if you are following this simple interest rate model. So let us bring in our compound interest rate model, which will not have this problem, because the interest is earned on the interest, or your interest itself earns interest. And in such cases, it's very simple. Year 1 is 1 plus I, year 2 this 1 into 1 plus I becomes the capital, and therefore you will multiply this with 1 plus I, and that is why you will accumulate 1 plus I square. In year T, it will be 1 plus I raised to T on the principle of 1 unit, correct. So that is our compound model. And if you look at the compound model and the simple model and compare them, there is a clear cut gap between the two. And as I mentioned in the last class also, this gap essentially diverges to infinity. Okay. So why should one use simple interest rate model? That's the main question, right? So the challenge or the advantage of simple interest rate model will be clear when you focus on the time interval of this length. Okay. So that's what we will discuss in the next few slides. So first of all, if time is greater than 1, time unit is greater than 1, then of course, as the graph reveals, the compound interest, which has shown the potential of exponential growth, is much better than the simple interest rate model. Okay. And now, as I mentioned, the crossover trap, which is 0 less than t less than 1, if I want to invest my money, and I go to a bank and I say I want to invest only for short span of time, for 6 months. So bank says we give same interest rate, 10% simple, 10% compound, both are same. you choose whether you want simple or compound. Okay, how will you answer that question? So now we have both models at our disposal. So let us understand that. So if I use the simple interest rate model for 0.5 years, the rate of interest is 10% and I will get 1.05 for 6 months. However, if I choose compound interest rate models, what I am getting is not 1.05 but it's 1.0488. Now, this is basically revealing the difference when I have 1 unit of time. Suppose you have 1 million rupees, 10 lakhs, then this interest, this change is significantly different, right? So which one you should choose? The verdict should be you should go with simple interest rate, because simple interest rate pays you more for fractional periods. Therefore, you will go for simple interest rate. And how this becomes more prominent is because of the convexity of this interest rate curve. So though it is not clearly visible, I will try to zoom it in this, so that it will be slightly visible. So let me go to the zoom settings. I will zoom in. So if you can see this, over the period 0 to 1, the compound interest curves actually lies below the simple interest curve, and that is where you have a potential for simple interest to magnify, right. So this is very evident, and therefore you should always choose simple interest over compound interest whenever you have a time period which is very short, less than 1 year or less than 1 unit. So simple interest always works better. So the simple, if you want to do the detailed analysis, you can see the simple line, the simple interest, the line that has simple interest connects the points because it's a linear thing. So 2 points uniquely determine a line 0, 1 and 1 to 1 plus I. These are xy coordinates, and this is the line. And over this, so when you consider the compound curve, the convexity property says that if the curve is convex, then it will lie below the line. So that's what the geometric property, the chord connecting 2 points on the convex curve lies above the curve. So the curve will lie below the line. Okay, so that's the property that rules here, and that is where sometimes the mathematical intuition is more preferred, because we are dealing with 1 plus I raised to t, that exponential curve. This, so in particular, if you want to simply understand the summary, it is given in the table, which is for 0 less than t less than 1, simple interest rate will earn 1 plus 0.5 times I, which is greater than 1 plus I raised to 0.5. If t is equal to 1, both are same. If t is greater than 1, then definitely you will go with compound interest rate, as it pays you higher pays. Okay, so that's the idea. And now, given this problem, I have made it very clear. So if you look at this problem, you withdraw a deposit after 9 months, bank offers 8% simple or compound 8% compound. Which one will you prefer, right? So option A, the simple interest rate will pay me 1060. Option B, the compound one will pay me 1059.22. So I will definitely choose option A, which is simple interest model. So the simple interest model is not useless model. If you want to invest for shorter periods, choose simple interest. If you want to invest for longer periods, choose compound interest. That's the verdict that we have given. So, key takeaways are: simple interest is linear, its effective rate decays over time, as I have shown in one of the slides. Then compound interest shows exponential growth, its effective rate is constant, it does not decay, and that is why you will always choose compound interest whenever the time period is greater than 1 year or one time unit, one period. Okay. But if you have fractional years where the time component is less than 1, then the simple interest rate will yield more than compound interest rate. So, with these takeaways, we finish today's class, and in the next class, we will try to master the dimension of time that money had shown, and that will be done by defining two new concepts. One is the present value of the money, and the second one is the discount rate D. Thank you for listening to me. See you in the next lecture. Thank you.